Hello students, we have studied in our last lecture about Weston's bridge circuit. In that we have studied that if the current flowing through this branch where the galvanometer is connected, that is along this diagonal, sometimes in place of galvanometer there can be a resistor also. Now if the current flowing through this branch is 0, then in that case this ratio of the resistance, that is R1 upon R3, will be equal to the ratio R2 upon Rx. Or if in a reverse way or in a vice versa, we can say that if this ratio is equal, that is if we found that the R1 upon R3 becomes equal to R2 upon Rx, then in that case we can also say that the current flowing through this branch will be definitely 0. That means no current will flow through this branch, and this is called the balanced condition of a Weston's bridge. And if the current is flowing or not along this branch, if we want to check it, then we have to connect a galvanometer. A galvanometer is a very sensitive instrument which can detect a very small current also. So with the help of this galvanometer, we can calculate the current flowing through it or current flowing through this branch. So this is a theoretical circuit of Weston's bridge. Now we are going to study about the practical circuit of Weston's bridge, which is known as meter bridge. So now let us see the practical circuit for the Weston's bridge. Students, you can see here in figure there is a wooden block. This is a wooden block, and these are metallic plates here, and even this L shaped, these are metallic plates. Now here in between these 2 points we can connect a resistor. So here there is one gap where a resistor can be connected. Even you can see on a right hand side there is another gap where you can connect another resistor. Here on left side you can see a resistor R is connected, and across right hand side you can see a resistor S is connected. And here between these 2 clamps or points, we can say there is a wire. You can see a black color wire. The length of this wire from here to here is generally 1 meter, and we know that 1 meter is equal to 100 centimeter. Students, here at this point and another wire is taken and a galvanometer is connected, and from galvanometer a jockey is connected. Here it is a jockey. This jockey can slide over this wire. This 1 meter length wire is there. It is a resistive wire, and this jockey can slide over that wire. As the length of this wire is 1 meter, it is called a meter bridge. This instrument is called a meter bridge. Across these 2 points a battery is connected. Students, remember here this point and this point are not different points, they are the same points. Even this point as well as this point, they are not the different points, they are the same points only. because here a metallic plate is connected here, as well as L shaped on left side and L shaped on right side. So this is about the practical circuit. So now students, for what purpose this meter bridge is used? As we know that meter bridge is working on the principle of Weston's bridge. It is used to measure the unknown resistance experimentally. Means if an unknown resistor is given to you, then with the help of experiment we can measure the value of that unknown resistance. Now here you can see a figure. There is a wire of length 1 meter, that is 100 centimeter, and here there are two resistors. Now students, if the value of one resistor is given to you, then you can find the value of another resistor. So by using this circuit or the Weston's bridge or meter bridge, we can find the unknown resistors. Here in figure, these are the metallic clamps of L shaped on left hand side as well as on right hand side. I have written that this point is A, means even this point is also A. If this point is C, then even this point is also C. Here you can see there are 3 points and this is a metallic strip. So all these 3 points are nothing but they are point B. Across points A and C, a battery of EMF E is connected and there is a key to switch on or off. Now students, we know that in a Weston's bridge there are 4 resistors. Here in this figure you can see there are only 2 resistors, but even this wire is a resistive wire. So if we connect a galvanometer across this point B and this point D, then this point D divides this wire into 2 parts. One is this, that is having length L1, and the other is having this much length, that is 100 minus L1. Why it is 100 minus L1? Because the total length is 100 centimeter, and if this is L1, then this much will be 100 minus L1. Now here this is a jockey which can slide over this wire left or right side, and so we can say that by moving the jockey we can change the length L1 as well as this side length. If L1 decreases, if we decrease the L1 by sliding the jockey towards left side, then this side length, suppose if it is L2, then L2 will increase. Or if we slide the jockey towards right hand side, then length L2 will decrease and L1 will increase. And we have seen that concept of resistance of a wire. Resistance of a wire is directly proportional to L. So if the length increases, then resistance will also increase, and if the length decreases, then resistance will decrease. So by sliding the jockey, we can change this to resistance. So now I think you understand that here there are 2 resistance. Here this is 1 and this is second. So there are total 4 resistance now, R, S, even this resistance on the left hand side of wire, and on the right hand side. So students, by sliding the jockey we can make the condition, that is balanced condition, means ratio of the resistance will become equal, and we can take the ratio. If the current flowing through this galvanometer becomes 0, in that condition we can take the ratio R upon S is equal to resistance of wire L1 upon resistance of wire L2. Now here the wire between points A and C is having a uniform cross sectional area, and its length is L, and so its total resistance will be RCM into L, where this RCM is nothing but it is a resistance per unit length. So students, suppose if we are sliding this jockey over this wire, when we slide the jockey we can detect the current flowing through this branch BD, because a galvanometer can detect the current. So now students, if we slide this jockey over this wire, in that case we can check the current flowing through this branch BD with the help of this galvanometer. This galvanometer will show some deflection if the current is flowing through it. Now suppose by sliding this jockey on this wire, at some point, that is say at point D, if the galvanometer shows no deflection, means zero deflection, then we can say that the current flowing through this branch, that is BD branch, is 0. And if the current flowing through this branch BD is 0, then we can say that this meter bridge is in a balanced condition. And if it is in a balanced condition, then we can take the ratio R upon S is equal to resistance of this wire, that is wire AD, upon resistance of wire DC. So suppose if the balanced condition is obtained, then we have taken the ratio R upon S is equal to resistance of wire AD upon resistance of wire DC. Now students, we know that if the length of the wire is L, then its resistance will be RCM into L, where this RCM is resistance per unit length. So here we have seen that the total length is L, so total resistance will be RCM into L. But here we are getting the null point at this point D, and we have taken the length from A to D as L1. So what is the resistance of this wire of length L1? It will be RCM into L1. So we have taken here the resistance of wire AD is RCM into L1, and we know that if this length is L1, then what will be this length, that is D to C. We have seen that this whole wire from A to C is of 100 centimeter, and so length of this much wire will be 100 minus L1. So here we have taken the length of wire DC as 100 minus L1, and so its resistance will be RCM into its length. Now if we are supposed to find the unknown resistance R, suppose this R is to be obtained, this is unknown. So in that case we can make the subject R. This S will be in the numerator of right hand side. So it is here. RCM will cancel. Remain will be L1 upon 100 minus L1. So we can obtain this equation for a meter bridge to find the unknown resistance. Practically we can measure the length L1. So with the help of experiment we can obtain this value, and if value of S is known to us, then we can easily find value of R. So students, I hope you understood this. Now let us see one example related to this concept or this topic about meter bridge. Now example number 3.9. Students, here in a given condition it is given that for a meter bridge the null point is obtained at distance L1, which is 33.7 centimeter, which is given. So if the null point is obtained at L1 is equal to this much measurement, that is 33.7 centimeter, then we can take the ratio for a meter bridge as R upon S is equal to L1 upon 100 minus L1. Now we will put the value of L1. So by putting the value we will get the ratio R upon S is equal to 33.7, which is value of L1, and upon 66.3, which is 100 minus L1. And this formula which we have used here is already derived by us for this meter bridge. You can see here it is R by S is equal to this, or we can say this. So 33.7 upon 66.3 is equal to 0.508. Let us give this equation number 1. Now students, here next condition is that a resistor of value 12 ohm is connected in parallel with S. Means now here in figure initially only R and S were there. Now another resistor is connected in parallel with S, that is between these 2 points, and its value is given. So after connecting this resistor, the null point is changed, and now the null point is obtained at a distance 51.9 centimeter. Let us give that as L2. So once again we can take the ratio like R upon S, but now here there is one more resistor in parallel, so equivalent of this parallel combination. So we will take R upon equivalent resistance. So we have written that only. So R upon S equivalent is equal to L2 upon 100 minus L2 in a balanced condition. Now we know that equivalent of SEQ. We have the formula for parallel combination, that S equivalent is equal to 12 into S upon 12 plus S. So students, now I need not to show you this type of calculation, because we know that for parallel combination we can use this formula, and L2 is 51.9 upon 100 minus L2, that is 48.1. Now dividing 51.9 by 48.1 will get 1.08, and here on left side we'll put only R by S, you can see here. So this term other than R by S, that is 12 upon 12 plus S, will be in cross multiplication, that is here. Simple mathematics is there, you can easily apply. Now here R by S, what is R by S? So from this equation 1, we already obtained the ratio R by S as 0.508. So from equation number 1 we will put R by S as 0.508. Now you can see in this equation unknown is S only, and by mathematically we can obtain that S. A simple mathematics is there. So S is obtained to be 13.5 ohm. Here we want to find both the resistance, because two conditions are given here. So we can find both the resistance. Now when the value of S is obtained, using that value of S, that is this value in equation number 1, you can see here equation number 1 is this. So putting the value of S, we can find R. So R is obtained to be 66.86 ohm. So students, you need to sit with your textbook, a notebook and a pen, also a calculator with you, and try now only. Don't only observe the lecture, you have to try this type of mathematics at the same time. I hope you will get these results and you are able to understand this. Now our next topic is about potentiometer, topic number 3.16. You can see in the figure that there is a wooden board on which a potentiometer wire is connected from A to B. Here the wire is in this way from A to right side, then there is a metallic clamp, then once again wire is there, again metallic clamp, again wire, metallic clamp, and up to B. So if we can consider the length of this much from A to right hand side up to this, if it is 50 centimeter, then the total length from A to B is 50 plus 50 plus 50 plus 50, that is 200 centimeter. So here the length of the potentiometer wire is 50 centimeter. Points A and B, they are connected to the battery via key and a rheostat. This rheostat is used to increase or decrease the current flowing through the circuit. Now from this point A, we can connect the cells whose EMF is to be compared. So first we will we will see the comparison of EMF of two given cell. So from point A, the two cells are connected, their separate keys are given, and then their common point is connected to the galvanometer via rheostat, and there is a jockey which is similar to that of Weston's bridge. Students, here this is a battery of higher voltage than the cells which are connected here, that is EA and EB. So current will flow from the battery with higher voltage towards this side. You can see here in figure the positive of these two cells are also towards this side, but current will flow in this direction. It is because this battery is of higher voltage. Now this type of arrangement is made. This is a practical arrangement of potentiometer. Now let us see about its theoretical part. Now students, for what purpose this potentiometer is used? This device actually can obtain continuously varying potential difference between any two points which can be measured simultaneously. Means, if this is the potentiometer wire from A to C, then by sliding the jockey on this wire, that is from A to C, anywhere, we can measure the continuously varying potential difference between that two points, that is between point A and a jockey. So with the help of this instrument, we can compare the EMF of given cells, as well as we can also determine the internal resistance of a given cell. Now potentiometer, its principle is the potential difference between any two points of a potentiometer wire is directly proportional to the distance between that two points. Means which two points? It is between point A, and suppose the jockey is here at point N. So the length from A to N gives that potential difference. So potential difference is directly proportional to length. We have seen that in Weston's bridge, resistance is directly proportional to length, but here potential is directly proportional to length. So this is the principle of potentiometer. This is the experimental circuit. Now here a circuit shows a battery of higher voltage, because this battery should have higher voltage than the battery with EMF epsilon 1 and EMF epsilon 2, and these two cells should be connected in opposing condition with this battery. You can see the positive of this battery is towards this side, as well as the positive of these two cells having EMF epsilon 1 and epsilon 2 are also in that direction only. So this type of condition is called opposing condition. Students, here also wire from A to C is of uniform cross section, and so according to principle of potentiometer, EMF of the cell is directly proportional to length, and if we'll remove the proportionality sign, then we have to put some constant, and so epsilon, that is EMF, is equal to phi into L. Here this phi is the potential drop per unit length. It is potential drop per unit length, we have seen in Weston's bridge that resistance is directly proportional to length, and so we have written that R is equal to R centimeter into length will give the resistance of the wire of length L, where that RCM, which was constant, called a resistance per unit length. Similarly, here this phi is a potential drop per unit length, because here we are going to find the potential difference or potential across the 2 points. Now, in the process of comparison of EMF of these two cells, what we will do, we will first connect cell with EMF epsilon 1 and we will disconnect this cell with EMF epsilon 2. That means we will only connect first cell via key 1 3. So only this much path is connected. This 2 3 gap is remained as it is. So when this point 1 and 3 are connected with each other, we can say that the cell with EMF epsilon 1 is connected. Now students, what will happen? The current which is from the battery will flow from this cell and it will move in this way from the galvanometer and then to the point N via jockey. Here from point A there is current here also in this direction, and so it will reach here and this closed circuit is formed. You can see here a closed circuit is formed. So at present, suppose some current is shown in the galvanometer, but by moving the jockey on this wire, at some point the deflection of galvanometer will become 0. Means we can say that the balanced condition is obtained. In that case, we can say that the potential across point A to N, that is for this much length, that is A to N1, will be equal to the EMF of cell epsilon 1, because EMF is directly proportional to length. So for this condition, that is when first cell is connected, we can write phi L1 minus epsilon 1 is equal to 0, that is epsilon 1 is equal to phi L1. Now students, here we have applied Kirchhoff's loop rule and we will obtain this equation, and after this step is obtained. But we can also write directly this step, that is EMF is equal to phi into L1. As I said, a loop is formed here. Here a loop is formed from A to epsilon 1, point 1, 3 galvanometer, point N, and again to point A. So if the loop is there, we can apply the loop rule, and so we obtain this equation. Let us give this equation number 2. Here we have used the principle of potentiometer also, because potential drop is phi L, and so it is here for point A to N1, the length is considered as L1. Now this cell is disconnected and the second cell, that is this cell having EMF epsilon 2, is connected via key 2 3. So this connection is made and this 1 3 connection is removed. So now what will happen? The current from the battery will move from the cell of EMF E2 to point 2, then 3, and now to the galvanometer. But as this cell has different EMF than the cell with EMF epsilon 1, we will get the null point, that is balanced condition at some another length. Suppose we got the null point at point N2 on the wire AC. So the length of the wire is considered from A to N2. Let this length is L2. So similarly, for cell with epsilon A2, we can apply the loop rule, and again we will get the similar equation which we obtain in equation number 2, that is EMF of second cell, that is epsilon 2, is equal to phi L2. So now students, let us give this equation number 3. You can see the equation number 2 and 3 taking ratio of these two equations. Epsilon 1 upon epsilon 2 is equal to phi L1 upon phi L2, but on right hand side phi is common, so phi will cancel and we'll get ratio epsilon 1 upon epsilon 2 is equal to L1 upon L2. So we have compared the EMF of two given cells in terms of the length of the potentiometer wire for balanced condition. Now students, practically we can find this length, and if EMF of any one cell out of these two given cells, if the EMF of any one cell is given, then we can find or determine the EMF of other cell. Now next part of use of potentiometer is about measuring the internal resistance of a given cell. Students, we know that internal resistance is denoted by small r, and we have also studied that every cell has its internal resistance, and we also have that formula that V is equal to epsilon minus IR. Here epsilon is EMF, V is a terminal voltage, and this small r is a internal resistance. Students, here only one cell is taken because we want to find the internal resistance of this cell. In earlier topic, it was a comparison of two cells, so we have taken two cells. Here this is a battery with higher voltage as usual. Between point A and C, this much is a potentiometer wire, and the positive of this cell whose EMF, whose internal resistance is to be obtained, is towards the positive of the battery. That means in opposing condition always. Here this is a rheostat to change the current or the voltage. This is key K1 to switch on or off, as well as there is a resistance box connected in parallel with this cell whose internal resistance is to be obtained. So a resistance box is connected in parallel with key. Then this much part is again similar. A galvanometer is connected here, and there will be a jockey which can slide over this entire wire to get the null point, that is balanced condition. So now students, what is the process to obtain the internal resistance? Here first we will keep this key K2 open. This key, if this is open, means this resistance box is not connected, and so the current will pass through the battery to point A, then to this cell of EMF epsilon, then towards galvanometer and to the jockey. So now suppose in this condition the galvanometer shows some current, but by sliding this jockey on the wire, at some point we can get the null point, that is current in the galvanometer becomes 0. So balanced condition is obtained, suppose at point N1, and so length of the wire from A to this N1 will be this much. So always length is considered from point A to the point of the jockey where the null point is obtained. So now with key K2 open, RB, that is resistance box, is not connected. So according to principle of potentiometer, epsilon is equal to phi into length L1. Here what is L1? L1 is nothing but it is the length of wire from A to N1 when the balanced condition is obtained. Now key K2 is closed. So now current will flow from this resistance box also. Also current will flow from here also and to this branch also. So now when this key 2 is closed, resistance box is connected in parallel with the cell of EMF epsilon. Now once again if we'll move this jockey, then suppose in this condition the null point is obtained at point N2. So if the null point is obtained at this point N2, then the length of the potentiometer wire from A is A to N2, A towards N2. This much length will be there. But students, as the null point is obtained, the current in this branch, this colored branch, will be 0. Means here the current is not going to flow because galvanometer shows 0 deflection, so there will not be any current. And so if here the current is not flowing, then the current will definitely flow in this part, in this loop. You can see here in this loop the current will flow. Current will not flow from G. So when the current flows through the resistance box, we get the terminal voltage. Initially we got EMF, but now we will get the terminal voltage when key 2 is closed. Length obtained from A to N2 is equal to L2. Initially it was L1 when the resistance box was not connected. Now it is L2 when the resistance box is connected, and in this case we will get the terminal voltage or terminal potential difference, and so V is equal to phi L2. Let us give this equation number 2. Equation 1 is also there, equation is 2, equation 2 is also here. So by taking the ratio of 1 and 2, we get epsilon upon V is equal to L1 upon L2. Phi will cancel out because it is common in both. Now, as I said earlier, epsilon is equal to I R plus R. Why? Because earlier we have seen that for the EMF, epsilon is equal to V plus IR, or we can write the equation in terms of V, which is equal to epsilon minus IR. So here we will use this. In that case, what is V? V is equal to IR, resistance of resistance box, plus I into small r. What is common here? I. So if we take out I common, then I in bracket R plus capital R. So epsilon is equal to this, and what is V? V is equal to IR according to Ohm's law. This V is equal to IR. So putting that values of epsilon and V, will get this term. I will cancel out, and after simplification, making the subject R, we will get this equation. So students, here simply we have taken the ratio and we have kept this for EMF and for terminal voltage using Ohm's law, and then simplifying, we get the formula for the internal resistance. Now students, practically we can measure the lengths for the null point, as well as what is the resistance in the resistance box, that can also be measured. So all the values can be measured using experiment, and putting that values we can find the internal resistance R of a given cell. Now example number 3.10. Here in this example we want to find the potential across points A and B. Here a potentiometer wire is given from A to C. This is a potentiometer wire, and the resistance of this wire, that is total resistance from A to C of the wire, is given that it is R0. The battery of voltage V is connected across points A and C. Also a resistor R is connected from point A, and a jockey is there. The jockey is placed exactly at the midpoint of AC, and so it is clear that if this B is the midpoint of AC, then the resistance of wire from A to B will be equal to the resistance of wire from B to C. And so as these two resistors are same, here we have taken that resistance from A to B as R dash. So from B to C also it is R dash, because this B is a midpoint. So here I have shown an equivalent circuit also, or equivalent figure also, so that you can easily understand. Now if this is R dash, then what is R dash? It is half of R0, because the total resistance from A to C is R0. So for half of the wire, the resistance will be half of R0, and we have taken that as R dash. Now students, we are interested in obtaining the potential difference between points A and B. So whatever the potential is across this wire, same potential will be across resistor R, because they are in parallel. So we can find the potential across resistor R. Let us take that potential as V1. That is, this potential as V1 across point A and B. And the potential across B and C is suppose V2. Total potential is V. So what is V? V is equal to V1 plus V2. So students, to obtain the potential across A and B, that is V1, we will do this process. We know that in parallel combination, the formula is like this. So here also, you can see in this equivalent figure, between points A and B, R dash and R, they are in parallel combination. So first we will find the resistance across points A and B. So as R dash and R are in parallel, we can write R dash into R upon R dash plus R. Let us give this equation number 2. Equation number 1 is this, that is for R dash. Now what is resistance between A and C? From figure you can see here, this is point A and this is point C. First we have obtained the resistance between A and B. Now between A and C, we know that this resistance plus this resistance, because both are in series. I have shown here equivalent figure, that from A to B we obtained RAB, that is equivalent resistance, because they are in parallel. So we have used this formula. So now it is RAB between A and B. Between B and C it is R dash, and both are in series. So resistance between A and C is taken as RAC, which is equal to RAB plus R dash. But what is RAB? From equation number 2, it is this, R dash as it is. Now R dash is here also and R dash is here also. In both the terms R dash is common, so we have taken it out. So in the bracket it will remain this, and after simplification, that is taking LCM and all, you can find this. So do this type of mathematics yourself. You will get resistance RAC. Let us give this equation number 3. Now students, what we are actually doing, we are first finding the current, because if the current is known in this path, then we can find the potential across this resistance, that is V2. Potential of the battery is V. So if this is obtained, that is V2 is obtained, we can easily find V1. So that's why we are first going to find the current I. And to find that current I, first we will find the total resistance between point A and C, and that we have obtained. Now further, we know that from this figure you can see that current is I, total voltage of the battery is V, and total resistance, that is equivalent resistance, is RAC. So according to Ohm's law, we can write I is equal to V by AC. Let us give this equation number 4. Total current is obtained. Now if the total current is I, then this current I will flow from this resistance, that is RAB also, and also from R dash. So what is potential across R dash? So again, according to Ohm's law, potential across R dash is equal to V2. V2 is equal to I R dash. V2 is equal to I R dash. But what is I? That we have obtained here from equation number 4. So I have used that only here in place of I, and I have given this equation number 5. So V2 is obtained here. but we know that total potential V is V1 plus V2, that is this V1 plus V2 is the total potential. And so if we make the subject V1, which is to be obtained, which is asked to find, is V minus V2. You can see that here, if we make the subject V, then this can be towards left side, so it will be V minus V2. Now V as it is, and what is V2? So it is this, equation number 5. So putting that here, in both these terms, V is common, so we have taken it out. So what is remained in the bracket? 1 minus R dash upon RAC. So RAC now. What is RAC? So from equation number 3, RAC is this R dash in bracket 2R plus R dash upon R dash plus R. So using that value here. And then students, you can see R dash cancel. And this term which is in the denominator of denominator will be in the numerator. So we have done the same thing in next step. Taking LCM, we will get this step. And finally, what is R dash? It is R naught by 2. So in place of R dash, we have taken R naught by 2, which was equation number 1. And then again, simple simplification is that is taking LCM, we get this final result. So students, I hope you understood this. You have to sit with a pen and a paper and you have to do the calculation with me. Then only you will be able to understand this. Here students, remember, whatever the variables we have taken extra, that is to be removed. Means here R dash was not given, but we have taken for simplicity. There was no RAC, we have taken that RAC. We have taken RAB. So whatever the variables which we have taken for simplicity to make the calculations easy, finally in the final result there should not be these variables which we have taken. Only those variables should be there which are given. So what are given here? Here V was given, R naught is given, and R is given. Nothing else was given. So our final result is also in terms of these variables, that is V, R naught and R. You can see here in the final result there are only those variables which are given. There is V, there is R and R naught. So here we complete our chapter number 3. Practice the examples of the exercise also, and also watch the video second time or third time if you are not able to understand.